So chapter 8, section 5 is using properties of trapezoids and kites. So we're going to talk about trapezoids and kites. Trapezoids and kites are both quadrilaterals. They're four-sided figures, but they are not parallelograms. So these two things that we're talking about today are not parallelograms, but they are quadrilaterals. They have four sides, but they're not going to look like our normal two sets of parallel opposite sides. Okay. So a trapezoid is a quadrilateral with exactly one pair of parallel sides. You can see in this one, it's the top and bottom, like in this picture. But I could draw it another way. I could draw it so it's on its side, and it would be left and right. One pair of parallel sides, not two. If it had two pairs, it would be a parallelogram. This is a trapezoid. Each of the parallel sides is called a base. So we're going to call them like base 1 and base 2. So there's base 1 and base 2. It doesn't really matter which one is which. There are two bases. The non-parallel sides we call legs. So you got the legs on the left and the right. You know the legs. You can differentiate them because the bases are parallel, the legs are not. Base angles of a trapezoid are two consecutive angles whose common side is a base. So notice that I know these down here at the bottom, the A and D, angle A and D, are definitely both base angles because they're both attached to the same base. B and C are base angles because they are attached to the base. They are the angles that are attached to the base. So find the parallel lines, attach to the parallel lines, you will find base angles. Like to call B and A, while B may be a base angle and A may be a base angle, they are not base angles together. We refer to those base angles together like B and C are a pair of base angles. A and D are a pair of base angles. They are attached to the same base. Like we can't call it a parallelogram because it's missing all of the criteria that we need. We don't have like opposite sides congruent. We don't have two sets of parallel sides. All of those things don't match up. But it does match a quadrilateral because it's four sides. Okay, now we've got an isosceles trapezoid, and this is going to be the one we're going to deal with a lot. If the legs of a trapezoid are congruent, like they are in this picture, the trapezoid is an isosceles trapezoid. So when we're talking about trapezoids, we know that all of them have one pair of parallel sides, but this one has one pair of parallel sides and a pair of congruent legs as well. Now, not every trapezoid has that. This is a special kind. It looks like almost like an isosceles triangle if we would draw the top on it, but this is an isosceles trapezoid. Okay, so here are some things that will be true of isosceles trapezoids. First of all, if a trapezoid is isosceles, if it is an isosceles, like I see that those two legs are congruent, then I know it's an isosceles trapezoid, then each pair of base angles is congruent. So imagine it's kind of just like an isosceles triangle that these base angles are congruent, but also the other pair of base angles will be congruent to each other as well. So these two will be congruent to each other, and these two will be congruent to each other. Yes, ma'am?
I hate to ask this, but can you remind me what isosceles means?
Isosceles is like, so in a triangle, if we have an isosceles triangle, we have two or more congruent sides, just like that. So if you notice that the trapezoid down below kind of looks like that if we chopped off the top of it. If we were to chop off the top of the triangle, what we would get is, if we did it with two parallel lines at least, we would get an isosceles trapezoid. And ultimately what we're talking about is, how do I know this is an isosceles trapezoid? Because of these two lines right there. Those two legs are congruent, therefore this is an isosceles trapezoid. So the base angles are congruent, just like they would be in an isosceles trapezoid, but it's on both sides too. So if a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. So let's say that you didn't know this. Let's say that you didn't know this piece of information right here. Like you didn't know that for sure. But I see the parallel sides. I know it's a quadrilateral, so I go, okay, this is a trapezoid. And then I see these as well. Well, now I'm definitely sure that this is an isosceles trapezoid and that the legs have to be congruent. Bless you. So the one pair of base angles being congruent is enough to say that this is an isosceles trapezoid. So we're kind of looking at it from both directions here.
Wait, can you save it?
Sorry?
Can you save it to copy?
Can I save it?
No, can you like save for a second?
I'll stay. I still have another thing to do on the screen. So,
Oh.
a trapezoid is isosceles if and only if its diagonals are congruent. So that works both ways. If I tell you this is an isosceles trapezoid, then I know that the diagonals, the entire diagonals, are congruent. What did I not say about the diagonals in this case that we've been saying about all of the parallelograms? All the parallelograms have something special about the diagonals that I didn't say here. Yes, sir. Well, that's not true for all parallelograms. There's something else about the diagonals that's true for all of them.
But they bisect.
They bisect each other. That is not the case in these trapezoids. We cannot assume that they bisect each other, but we can assume that the entire line is congruent. The entire red line is congruent to the entire red line. That part will be true. Yes, ma'am.
Is there ever a time where they won't bisect each other?
It is possible that they can be depending on how the trapezoid look. Well, no, actually, because if we had that happen, what we would actually get is a parallelogram. It would force it into the shape of a parallelogram. So we're saying the whole line. Now, again, that's different than bisecting. A lot of people are going to start bisecting it, and that's true for parallelograms, not for trapezoids. Okay, now we're talking about the midsegment. So midsegments, remember, go from midpoint to midpoint. The midsegment of a trapezoid is the segment whose end points are the midpoints of the legs. What they mean there is that here's the midpoint of a leg, here's the midpoint of a leg. I know that because it's congruent on both sides. The midsegment looks like this. It's the line that connects the midpoints on the legs. So make sure that we're talking about legs. Because it's going to be very important here about the three lines. We're going to look, something special is going to happen with these three lines. All right, this is the trapezoid midsegment theorem. And what it says is the midsegment of a trapezoid is parallel to each base. What they're saying is that if that blue line in the middle, xy, is the midsegment, then it must be parallel to both of the bases. It has to be parallel to BC on top, and it has to be parallel to AD on the bottom. Like, we already knew the bases were parallel, but that tells us that this will be parallel to those as well. All three of them are parallel. And the length of the midsegment is 1/2 the sum of the lengths of the bases. Meaning, if you were to take base 1, however long it is, and add it to base 2, however long that is, and then take half of that amount, that's how long the midsegment would be. It is half of those two things. So we're going to add those together. Now, we're going to use this as an idea. Notice I wrote it out as a formula there. I'm not just saying it's just half of adding those together, because sometimes they might give me the midsegment and one of the other bases, and I might have to play around with some x's to figure it out. Like, we're going to figure out the piece that we're missing. But ultimately, you can see here, if you were to take BC, which is one base, and AD, the other base, and add them together, and then divide by 2 or multiply by 1/2, whichever you prefer, they're the same thing, then you would get the length of the midsegment. This line right here is half the length of the other two lines added together. Add the other two lines together, it is half that length. All right, a kite is not a trapezoid. If you notice, it's also not a parallelogram. It doesn't meet those opposite sides being congruent. It is not the same thing. So this is a quadrilateral. It's a four-sided figure. It's not a trapezoid. And it's not a parallelogram. So it's its own thing called a kite. How do you recognize it? Because it kind of looks like a kite. Like it looks like what we would be like a very generic kite that you would go out flying. A kite is a quadrilateral that has exactly two pairs of, so important that you underline this part, congruent consecutive sides. Meaning the sides that are right next to each other are the ones that are congruent. Like this dude and this dude are congruent. And this one and this one are congruent as well. Yes, ma'am.
How do you tell, like, if that one's next to it? Because AB is also next to BC, so how do you know that?
What's going to happen is in every scenario, when you do it even like upward or downward, you're going to have two lengths like this that will be congruent, and the two right next to each other that will be congruent as well. And I'm going to help you show you some things. We're going to talk about some angles in a minute. It'll help you identify which ones are congruent as well. So she's saying, like, she's looking at this and she goes, why was it AD and AB? And like, instead of being like, well, these two are right next to each other, why couldn't it have been them? And granted, we're all looking at this and being like, oh, wait, because look, they're marked that way. But what if they weren't marked that way? And somebody said this is a kite. How would I know which ones are congruent to each other? We're going to get to that, so don't worry. How do we identify which are the congruent ones? And there are some other things about the angles that are true in this as well. All right, here are some things that are true about kites. If a quadrilateral is a kite, then its diagonals are perpendicular, meaning what? They make 90-degree angles. So check out what we get is we get a whole bunch of right triangles. We get 4 right triangles, which is useful. Maybe we could Pythagorean theorem them out. Maybe we could 30, 60, 90 them. If you notice, there's also, look at this, there's an isosceles triangle right here. Maybe we could use the base angles theorem to find out some angles there. And there's also an isosceles triangle here. So as we go through, those are things to keep in mind, is that we've got 4 right triangles there. We have 2 isosceles triangles, and they're all right triangles. All 4 of those are right triangles. Some useful information. As soon as you say kite, I know that to be true, that those diagonals are going to be right angles. Now, did it say that they bisected each other? No, that's not something that we've got here. We don't have them bisecting each other. We also don't have the diagonals equal to each other like was true in the isosceles trapezoid. All right, if a quadrilateral is a kite, then exactly 1 pair of opposite angles are congruent. 1 pair of them will be congruent, not both, meaning that 1 pair are congruent to each other. If these 2 are the ones that are congruent, then angle A and C are not congruent to each other. They're not. Now, you might be like, how do I know which ones are the ones that are congruent to each other? So check it out. Notice that these 2 are the congruent sides here, and these 2 are the congruent sides here. It's always the angle where the 2 non-congruent sides meet up. Like, notice that this one and this one are not congruent to each other. Where they meet up is an angle. Over here, there is a non-congruent side and a non-congruent side. Where they meet up is another congruent angle. So, if I could use that both ways. If I see 2 non-congruent angles, let me just draw this another way. If I see this shape right here, and the information is given to me that this is congruent to this and this is congruent to that, I know that this angle right here between the 2 non-congruent sides must be congruent to that one. Or vice versa. Let me draw this a different direction. Let's say I've got a kite that looks like this, and I see that the left and the right are congruent to each other. That must mean that that angle is in between the 2 non-congruent sides, allowing me to do that. So the angle helps me find the congruent sides. The congruent sides helps me find the angle.
Isn't there like a long way that you could do, like, in terms of like finding the actual angle of it, like with the first theorem on that thing, with like using base angles?
Well, we would still need some more information, because even with base angles theorem, like, we don't have any other angles but those 90s there. And the 90s are not part of the isosceles triangle. So once we have some numbers, we can start doing some other things. But you'll see once we start doing some problems that that piece of information will also be helpful. Alrighty. Okay, we need to find the measure of angle A. Now, let's talk about this for a minute. We need to identify, what is this shape? What is it? Is it a quadrilateral? Yes, it definitely has 4 sides. Is it a parallelogram? No, that's out. So like everything that we did before today, all of those are out, except for today we got down to 2 other shapes, trapezoid and kite. Is it a trapezoid? It's definitely a trapezoid, but more specifically than a trapezoid, that's a very specific kind of trapezoid called a what? An isosceles trapezoid. And what is true about an isosceles trapezoid?
Two or more sides.
The base angles are congruent. So right away, give me one other angle up there that you know right away. Which is where? Angle D is 100. Now, I'm going to show you a couple different ways how we could address the other angles in there. That is enough, having that one angle, to address every angle in there. First of all, and people generally tend to like this better, parallel line, transversal coming across it. What's true about these two angles? They're supplementary. So angle B has to be what? 80. That has to be true. So if B is 80, since this is an isosceles trapezoid, what's true about A? Base angles theorem. Again, that's 80 as well. Now I'm going to show you another way you could have done this. And it's not using a parallel line in the bottom. There's another way we could have done this. Okay, so we've got... Let's go back to when we were here. This is going to be a really rough sketch here. I'm not trying to make it pretty. Okay, so when this was 100, and you then told me right away that you knew this was 100, you're like, okay, base angles. And you're like, well, what's the other one? Okay, let's say I'm stuck and I don't remember how to do the other angles. This is a quadrilateral, a four-sided figure. How do I know how many angles in total, how many degrees in total should be inside? Don't give me the number. I want the how do I know.
Isn't that
N minus 2 times 180 to find the total amount of degrees that should be in there. That's 4 minus 2 times 180, or 2 times 180, which gives me 360 degrees in total. In total, I should have 360. How many of those have I accounted for so far?
Oh no, 200.
I have accounted for 200 of that 360 already, which leaves me with 160 degrees, which I know has to be evenly split between them. So 160 divided by 2 gives me the remaining 80 degrees and 80 degrees. Amber.
I thought that you could only do that equation when you have a regular quadrilateral, and we don't know that it's regular because we don't know that.
No, well, so that's how much, you can only do the, how much is each angle on a regular one, because each angle is different here, right? That's not each angle. Each angle is different.
Well, that's
How
just
to
the
find the degrees?
yeah, isn't the degrees of an angle?
Okay, so check this out. Like on a regular triangle, right? A regular triangle, would you agree that a regular triangle would look like this, yeah?
Yeah.
And it would be like this, yeah? And this.
Yeah.
Okay, how many degrees in total are in a triangle? 180, and we would split it up evenly amongst the three if we wanted to find each, which would give me 60 degrees each, right? Okay, so a regular quadrilateral, so every quadrilateral in the world has 360 degrees. A regular quadrilateral would have that divided by 4, which means that each angle would be 90 degrees. That's not the case here. That's not a regular quadrilateral. A regular quadrilateral would be a square. This is not a irregular quadrilateral. This is just a quadrilateral. And so I can tell you how many degrees there are in total, which may help me calculate. I go, well, I've got this much accounted for. Maybe that means that the others are something else that I can figure out. Bam, I went back to slide 9. Okay, what is it about? Okay.
Can you use the diagonals at all of this? Or
So what do we know about the diagonals of a trapezoid? Right, so it doesn't benefit us on this problem, but maybe on future problems it will. Yes, ma'am.
Speaking of diagonals, do they have any type of ratio to the lines?
So let's talk about how they're divided. It's actually kind of complicated and how they're divided up, but we'll get to that. What is it? What is it? That's so awesome. I understand it too together. We won't tell anybody else that we understand it. Okay. Yes, sir. Do you understand it too? I can go back. I don't mind. That's the great thing about PowerPoint. It allows me to go back. Watch this. All right. What kind? First of all, is this? And you're going to hear me ask obnoxious questions because I'm going to ask you to be very specific about what types of shape it is. So, is this a quadrilateral? Yes. Is it a parallelogram?
No.
Is it a trapezoid?
Yes.
Is it an isosceles trapezoid?
Yes.
Okay, so we've identified all those things. So now we need to find the measure of angle F. Again, basically the same problem we just did, but in a different order. Somebody talk to me.
Okay, so we know that angle E is 49 degrees because it's another corresponding case angle. And then we know that FG and EH are parallel. So, what's it called? So yeah, just do the so then put a transversal for EF.
Okay, and remember, she had a couple ways she could go. One of them is not better than the other. We're just looking at there. She wants to do it as same side interior angles or consecutive interior angles. Nothing wrong with that.
And so we know that they're supplemented because they're parallel. So we would subtract 49 from 180, and then we come up with 139.
How much? I just couldn't hear you. That's all. Was it? What if I wanted angle G?
It's another base angle, so it's the same thing.
Let's say I was sitting there and I was like, and I'm doubting my numbers at this point. What is something I could do with all four numbers to like go, okay, that sounds reasonable.
Add them all together and they equal 360 then.
They better equal 360. If they don't equal 360, something's wrong. Because we know in every quadrilateral, the sum of the interior angles should be 360 degrees. How did we know that? Because n minus 2 times 180.
And minus 2 would just be minus 2 times 180 plus everything.
Every polygon. Like, well, because a polygon is made out of straight lines, right? Like sometimes people say shapes, and I don't want to say shapes, because like a circle is not a polygon. So we get into like sides, and you go, okay, like this is a shape right here. It is not a polygon. My rule doesn't apply to that. Like it applies to all polygons. Straight lines, closed figures, you know, all those things that don't cross over each other that we learned about polygons a while back. Okay, so now we've got some diagonals. So clearly something's going on in here. Yes, ma'am. Hold that thought. Okay, so what gave it away? Tell me the things that went like that you just, how did you identify it as isosceles trapezoid?
Because there are two parallel lines, the top and the bottom.
Good.
But then there are also congruent sides.
Good. What do we call those congruent sides? What are those sides called? Okay, what are the parallel sides called? There's something about the
Base.
Okay, good. If those are the bases, what do we call the other things?
Legs.
Wow, that was so good. You sounded just like Dylan when you said that. It was perfect. Like your ventriloquism is getting so good.
Thank
Like
you.
I knew it was you, but you did a great Dylan impression there.
Okay. So it's an isosceles trapezoid, and we know that isosceles trapezoid, their diagonals are congruent to each other. So,
Beautiful.
sorry, hold on. KB is 21.9,
Okay, so here's KB.
and then MF is 32.7, which is the other line.
So let me just mark this real quick. I'm just going to just kind of do that. The distance from there to there, that line, is 32.7. The distance from here to here is 21.9.
And so we know that since it's an isosceles trapezoid, that the diagonals are congruent to each other.
Okay?
So since we have one full diagonal and then a part of it, they're asking for the other part, which is FB, which if we look at the other diagonal, it's also BJ.
Okay?
So we could do 32.7 minus 21.9.
Okay, let me just set that up as an equation. So she says this part right here, if I were to add it to 21.9, I would get the whole line. So what I'm going to do is like, so KB, I'm just going to do it letters first. If I took KB and I added BJ, I would get FM. So KB is 21.9 and BJ I don't know, and FM is 32.7. So doing a little math there, as she said, she jumped all the way to the end there. 32.7 minus 21.9 gives me what?
10.8.
10.8? Okay. Because the whole diagonal is congruent to the whole diagonal. Okay, the whole line is congruent to the whole line, which means that leftover part must be equal to the other leftover part. Okay, we have a kite. let's talk about, I don't even want to look at what they're asking me for. Let's talk about what we know about kites, because here's what I have found is a great strategy. Quadrilaterals get to be a kind of boring, hard chapter if you don't just look at things and go, okay, what do I know? Amber.
Well, we know that, well, at least I think, BC is congruent to CB.
Okay.
And BA is congruent to DA.
Okay. Anything else?
Wait, how did she know?
Well, in this one, I would never do it this way, by the way. But in this one, the picture, they really want you to use the picture for it. I am not a very big fan of just using the picture because if two lines look very similar, but in this case, they've drawn one obnoxiously longer than the other to make it stand that way. I'm not a big fan of that strategy because I think it makes you assume things, and you know me, I'm not big on assuming. Unfortunately, this is like one of the textbook ones, so I'm very critical of this one, but we'll go by what they did. They're going based on, they're saying that this picture it has to be drawn to scale if we're going to do it this way. Otherwise, we wouldn't know that.
So now, based off of that, we know that angle B is congruent to angle D. The angle as a whole.
Let me answer your question, actually, the question you just asked based on something else, though. It says angle DAB, this one right here. DAB is right here. I'll dab to that. That's 54 degrees. And then it says that angle CDF, actually, you're right. We can't answer it right there. So you're right. I can't do it with the sides. I thought they were going to, if they had given me this angle, I could confirm that they were the ones. But that's what we know so far. And CDF is 52. CDF, this is 52 degrees there. George?
So we know that there's two triangles that we split it up.
Okay.
And the top triangle we have CDB, one of the angles is 52.
I'm sorry. You said I blanked there for a minute. What did you say? I'm sorry. Which one?
I made it into two triangles.
Okay.
The top triangle is BCD.
Okay, so he's looking at two triangles. This is what he's doing. This triangle right here. Okay, I like where this is going. And I assume the other triangle was right here?
Yeah.
Okay. He said, I'm going to look at this like two isosceles triangles. Huh?
No, AC and BD are perpendicular.
Ah, he knows that the diagonals are also perpendicular. That's a piece of useful information too. All these things are true. George, keep going. You had something though.
So we know that the red triangle is isosceles, so
Okay.
angle CBD is also 52.
Okay, so he's looking just at that red triangle there, and if he tilts his head a little bit to the right, he goes, oh, isosceles triangle. Base angles are congruent. This must be 52 degrees.
And then you just add them up and subtract by 180.
Okay?
You get angle BCD is 76.
BCD, this one, entire one up here. I should not mark that as congruent to each other. I got to give it 3 lines. I am not making, remember, this only has one pair of congruent angles, so I wouldn't expect that it's the opposite as the other one. That's 76 degrees. Is that the one we're looking for?
Yeah.
Oh, that was nice and easy. We didn't even need that 54 degrees. Now, let's pretend that I wanted BCF. I want to illustrate something. BCF. What if I asked you for BCF? And don't just tell me, oh, you just split it in 2. Don't just tell me that because that's not anything we've gone over.
So since we used the 52 and we know that BD and AC are perpendicular, we can just add 90 and 52 and subtract by 180.
Good. We have a triangle right here. That 76 is the whole big angle, so we could just go 90 plus 52 is 142, which would leave me how much for that remaining angle there? If that's 38, what is the other angle over here? 38. So it does give us a lot of information that we can figure out here. We can start to solve these triangles.
So like 76, 54, and then angle D and angle D are all gonna add 36.
So what's going to add up to 360 here is this 54 degrees, right? That's one of the big angles. This 76 here, and these two congruent angles right there, which do not do this. Just because that one got split up into 38 and 38, do not do 52 and 52. That just, do not say that's 104. But what we could do is say, well, what if I did want to know those angles? So check this out. We've got 76 and 54 in total. Now we know there's 360 degrees in total because we just did that a minute ago. So far we can account for, that is 130 degrees. Okay, so we are accounting for 130 of the 360, which means there's 230 degrees to split between those two angles there. If I split that in two, I would get 100 and, how much? 115? So this whole thing here is 115. And I know it's congruent to this one here, which is 115, which would allow me to start solving these here. I can start finding this missing piece here. And then I would be able to see whether this one was split evenly in two. So lots of things I can do with that. You have to kind of move your way around. Don't try to jump right to the end. What do I have? Where does that take me? Amber.
I'm confused how you got that.
Which part?
The part that you just said, if I,
Well, we know, they didn't ask us that. We were done at 76 degrees.
no, I know.
But we knew there were 360 degrees in total. Why?
Because it's a quadrilateral.
It's a quadrilateral, and if you didn't know that, n minus 2 times 180. And then from there, they told us that this was 54 degrees.
Yeah.
And together, we figured out that this was 76 degrees. So 54 and 76 was 130 degrees. 360 minus the 130 we've already accounted for was 230. So there were 230 left for these two congruent angles right there. So I split it in two because they're congruent. Then the 115 took me even further. So there's a lot going on here. We got to work through them. All right, Lucy is framing a kite with wooden dowels. So she's literally just laying wooden rods across some paper and or whatever, plastic, I don't know. She's trying to make an actual kite. She uses two dowels that measure 18 centimeters. So here's 18 and 18. The dowel that measures 30 centimeters. So 30 centimeters, by the way, that they're saying it goes from left to right. They're talking about this. That's 30 centimeters. Two dowels that measure 27. That's this and this. To complete the kite, she needs a dowel to place along KL. So she needs to know what that is. So what we've got here is she needs a dowel to place along. She has a dowel that is 36. Okay, the dowel that she has is 36 centimeters long. How much wood will she have left after cutting out the last dowel? So she's going to cut something out of it, and then we want to know how much is left. And what is she going to cut out? She's going to cut out KL. So we need to figure out what KL is. Talk to me about strategy.
Well, I use Pythagorean theorem.
Oh, well, you jumped a whole lot of steps then to get to Pythagorean theorem. You got to talk to me how you got to Pythagorean theorem, because I would say there's at least two things you have to explain to me before you got there.
So since the diagonal are perpendicular.
Okay, that's good. I definitely needed to hear that, because I'm not hearing Pythagorean unless I see this.
And then find the bottom JM is 30, so it'd be 15.
That's a bold statement. Why is that 15 and 15? How is it in the, how do I know it's in the middle? I'm okay with it being in the middle as long as you can. It's a perpendicular bisector. How do we know it's a perpendicular bisector? That's the big question, because I feel like we just say that sometimes. We're like, probably perpendicular bisector. But the question is, there's something that tells us it is. Colette. Oh, sorry. I'm sorry.
Because it goes from K to L and then it forms a 90-degree angle, and so which means they have to be a line with each other.
K to L and forms a 90-degree. I'm slightly confused. I don't know what you mean.
In terms of you see how it goes, it goes straight down, and so it forms a 90-degree angle. And if it were to be anywhere else in terms of other than half, then it wouldn't.
Okay, check it out. That forms a 90-degree angle, right? But I didn't split it.
It goes, here's the
Okay, talk to me.
So, since the perpendicular bisector, I forgot what they call the sides, but since 18 and 18 are congruent,
Okay.
that's what happens.
Since this point is equidistant
There you go.
from the endpoints, it must lie on the perpendicular bisector. So not only was it perpendicular, it is a bisector. So I'm okay with that. We just needed to identify why. Because the thing is that we get so used to saying, it's probably just this. And you're probably just right, but probably won't help you when it gets down to like, what if this were a proof? Okay. So we need the whole length of KL. And even if we find the whole length of KL, we're not done because that needs to be subtracted away from a larger piece. So let's go back. You were talking to me about Pythagorean theorem.
Okay, so you can split into two triangles.
Okay, so we're going to look at this line first, yeah? He's saying let's address this in two separate right triangles. So he can look at this upper left or he can look at this upper right. It's the exact same triangle, so it doesn't really matter which one he chooses.
And then you can do 18 squared minus 15 squared, and that would get you
Okay, I'm going to do exactly, you're not wrong, but people are going to be confused as to why you did that. So he's saying 15 squared plus x squared is equal to 18 squared. But what he did in his head was he had already subtracted away the 15 squared, like this. He did that. That's just what he's saying right there. So we get x squared is equal to 18 squared minus 15 squared. 18 squared is? Okay, so we get 324 minus 15 squared. Okay, so 225. And 324 minus 225 gives me? Got 99 problems, but a kite ain't one. All right. You guys give me the best pity laughs. You're like, huh, dad jokes. All right, let's keep going. Where are we going from here? Square it? Oh, square root it. That's totally different. Okay. X is equal to square root of 99.
And then you need to get
Isn't that
You
radical 11?
No, 32 times 3.
I just somebody help me out. Yes, ma'am.
So step of 5, you would do the square root of 9 times square root of 11. Step of 5, 3 times the square root of 11.
Perfect. 3 square root of 11. So this piece right here is 3 square root 11. You want to do the other one?
Yeah.
Okay, so there's another right triangle that we need because we need to get this piece.
And then 15 squared plus y squared equals 27 squared.
He called it y because he's already used x for the other one, so he's trying to differentiate between the two. In which case, he's doing it the long way for us, but I know that he's comfortable doing 27 squared minus 15 squared, which is 27 squared is 729. And we already know that 15 squared is 225. So 729 minus 225 is going to give us 504. All right.
Then square root.
Okay, and this is the place where everybody starts to groan. I'm going to tell you right now, I don't know off the top of my head what the largest square number that goes into it, but I know one. What's your question, Colette?
No, I was gonna say it, but then like.
Well, how'd you break it down? Okay. Okay, so check it out. I'm going to tell you right now a square number that I know that goes into it, and you tell me how I knew right away. And it's not because I have like some head for numbers. I know that this is divisible by 9. How did I know that?
You just added the numbers.
I added the numbers together. 5, 0, and 4 is 9. This is divisible by 9. That is a rule for dividing by 9s that you learned in elementary school that you might have forgotten, but that is a rule that if you add the numbers together, the digits together, and it's like 5, 0, and 4, that's 9. So check this out. Just to prove it to you, go to your calculator and do 504 divided by 9. This is 9 times 56. Now, did I go with the best one? Probably not, but at least I go, this cut it down a lot. What is that 9 going to become? Okay, now that 56 is probably going to have to be broken up, but that 56 should probably be familiar to you if you know your times table. 7 times 8. So we've got the square root of 8 times the square root of 7. Now, neither one of those help me, but one of them I feel like would break down. Okay, great. So we've got y is equal to 3 square root of 4 times the square root of 2 times the square root of 7. So we get 3 times 2 times the square root of 2 times the square root of 7, which equals 6 times the square root of 2 times the square root of 7. What should I do with the 2 and the 7? Put them back together because they're not going to break down anymore. So it's just going to go square root of 14. Y is 6 square root of 14. All right. This is not a problem that you would be able to do without a calculator. So because here's why. We know that the line KL is equal to, I got to give this a center letter here. So HIJKLM. So I'm going to call this N in the middle.
Wait, is the 6 square root of 14 the second part?
It's the bottom part, yep. Okay, so KL, that entire line, consists of, now I added an N to the middle, so if you didn't add this, it's not going to make sense. I just needed something to explain this. I've got KN, the top line, plus the bottom NL. So I'm just going to add those together. KL is equal to 3 square root 11 plus, and what did we say the other one was? 6 square root of 14. We are not capable of adding that together ourselves yet, but you could do that on your calculator. Do 3 times the square root of 11 and hit enter, and then do plus, I'm going to use some parentheses here so it doesn't get mixed up, 6 times the square root of 14, and I got 32.3998. So just for our sakes here, because we are going to do this in a calculator, let's just say that that's approximately 32.4. Let's just say it's 32.4, because let's round it to the nearest tenth, because that's a really long number. So, is that my final answer? No, because they wanted to know how much does he have left after all that. So, we're going to go, or she have left. So, it's 36 minus 32.4, leaving me with 3.6 centimeters. Approximately, yeah, because we used rounded numbers.
Hey, what did you do?
I did this in my calculator.
How did you get
Wait. We're not done with slides.
How did you get 3.6? Yeah, that's the last one.
Okay, wait, check it out. How did I get it? Because remember, it says right there, she has a dowel that is 36 centimeters long. In the very beginning, I said, remember, whatever answer we get, we're going to have to subtract that away from 36. 36 minus 32.4, it gives us 3.6. 36, the total dowel minus the dowel that we need, how much is left? 3.6 centimeters, approximately.
How did you do that on your calculator? Because when I did what you told me to do, I got an error.
Okay, well then I'll check with you, because remember I said use parentheses, so if you didn't use parentheses, it wasn't going to work out. So we'll look over that together. So yes, let me... Oh yeah, this is not... Yeah, sorry, I don't know why that's even in there.